Alright, hi everybody. Welcome to the last little bit of content that we need to review before the AP test. What we're going to look at today is rotational motion and torque, which is kind of a fun unit. It's a nice way to just kind of like recap everything that we've done, because what we're doing with this unit is just looking at what we did before and then saying, okay, what happens if we took these ideas and they spun, they rotated? So that's what we're looking at. And kind of our main objective today is to figure out how these tensegrity sculptures work. You may not know what I'm talking about, but I'll show you some pictures in a second. I keep on seeing these things pop up like everywhere in like the past couple of weeks. They are really cool. I think they're really neat, and they're super relevant to the physics that we're going to look at today. We'll figure out how these things work. It's these like floating things. People are making them out of Legos, and I keep on seeing them pop up on the internet. So I'm like, hey, let's talk about it. So what we're going to do today is a quick little introduction with those things. Then we'll look at reviewing rotational kinematics, torque and angular acceleration, angular momentum and torque, and then conservation of angular momentum. Then I'll give you some practice stuff, and I'll give you an FRQ. So practice to kind of get the concepts down in quick little short bursts, and then some FRQs to, again, practice the structure and, yeah, look at these in a little bit deeper ways. And that'll be due on Friday. And then just kind of coming up, I'm going to make a quick video about like, hey, what do we expect on the AP test? What do we need to do before to prepare? And yeah, just kind of like, hey, what's the structure look like? What do we need? What are we going to do? And yeah, and then next week we have a couple of final preparation things, but I don't know what that looks like yet. And then we'll take the test on, I think, Thursday for you guys, or the 14th, whatever that is. A Thursday? Wednesday. I don't know. And then, yeah. So what we want to start off looking at is these tensegrity sculptures. They're cool. They show up in like different sculptures or art or architecture. And really it makes use of this tension, this idea of tension. So it stands for tension and integrity. Like, I don't know, integrity is like ability to hold or something. I don't know, whatever. But yeah, so these are some examples. I was kind of like watching this video, and it just looks neat. It looks like this thing, these objects are just kind of hovering there. It looks like they're floating. So we won't watch this whole video, but I just kind of have a few. I'll just kind of skip through it. But it's neat. It looks like you're able to take these things and with 3 strings, with 3 wires, or yeah, anything, I guess, any kind of rope. It looks like you have these floating things, and it almost looks like it's like levitating. It looks like it's held up by magnets or something. But this is all working just from the tension. So it looks cool. You just take these. Like, how neat is that? And then it just looks like it's levitating. It looks like these strings are holding it up, but that's weird because we know that strings don't push. And yeah, the way to explain it is what we're going to look at today. Oh, this one's cool because they have like 4 in 1. That's crazy. Where's some other ones? This one's cool. Yeah, it's just real neat stuff. And it kind of, you look at it and you go, that looks like it's breaking physics, but we know that that's not possible. Not possible to break physics. So we'll look at that today. And then, yeah, you can make tables out of it or use it for art or whatever. But I think this table's neat. I would want a table like that. That'd be kind of cool. All right, but yeah, so what we're going to start off with is rotational kinematics. It seems kind of scary. We look at it and we have all these new like variables and these new like, pretty much that's it, new variables. But it's just us redoing everything that we've done before. So for this time, objects are rotating instead of just moving in a straight line. So to kind of start us off, when we did regular kinematics or linear kinematics, we looked at and we defined this position. We said, hey, we want to be able to define the position of an object because it'll tell us where an object is in space. And once we know where an object is, we can say, how does this position change? And that's really where most of our physics comes from. Like, hey, what happens when we change position? So when we did linear position, we measured it in meters. And yeah, it was helpful. We could say, hey, that object is at 4 meters away from 0. And that was great. That was something that was really helpful. Then we have this idea when we're spinning, we can define a quantity called the angular position. And the variable we're going to use for that is theta. And this theta, this angular position, is going to tell us where an object is in space when we're going around a circular path. And we're going to measure it in radians. So maybe you guys have used radians in math. It's just a way of kind of splitting up a circle and talking about what angle you're going at. So I kind of made this little Desmos thing. But if we have, let's just turn on one. if we have one object moving around in a circle, it's going to be helpful for us to say, hey, this is at pi over 2, or I guess this would be pi over 2. I don't remember. I don't know the unit circle. This would be, yeah, this would be pi. Hey, we're pi radians away from where we started. Or hey, we're pi over 2 radians away from where we started. Or we're 3 pi over 2 radians away from where we started. Or we're 2 pi radians from where we started. So it's going to be helpful to be able to quantify that and say, where are we? Where are we along a circular path? And then stuff starts to get interesting when we change that position. So when we changed linear positions, we said, okay, well, this change of linear position has this velocity that's associated with it. And we said v is our velocity, and it tells us an object's change in position over a change in time. Or in kind of more common terms, how fast is our object moving? And we had to define a few things because it was starting to get a little bit weird. But we had to say, okay, well, let's call right positive and left negative. So if we're moving to the right, we'll say that's a positive velocity. If we're moving to the left, let's call that a negative velocity. And then we measured this in meters per second. So how many meters did we change in a certain amount of seconds? And we can change our angular position just like we changed our linear position. And the quantity that's going to be associated with this is our angular velocity. And our symbol for that is omega. It looks kind of like a W, but it's a little bit curlier. And the angular velocity is going to tell us an object's change in angular position over time. So if we change our angular position, there will be an angular velocity associated with that. So we can think about it as how fast is an object spinning, or how fast is an object moving in a circular path. And when we want to define the directions of this, velocity has a direction to it. We'll say, okay, counterclockwise is going to be positive, and clockwise is going to be negative. And we're going to measure it in radians per second. So how many radians did we move over some amount of time, over some seconds? So we can have this again, and we said, okay, well, things start to get interesting when we're changing our angular position. So if this thing is spinning, we can count out how many radians does it take it to complete, or sorry, how many seconds does it take it to complete a rotation, to go 2 pi radians. We can measure that, we can talk about it, we can analyze it, and yeah, a lot of our physics comes from this idea of changing velocity, or changing angular velocity. And then, oh yeah, and then one kind of thing with that too, if we have more than one object, this is where stuff starts to get a little bit confusing. But we have these two objects that are at different radii, so 2 different radii along our circle. But if we look at these 2 objects, they have the same angular velocity. If we look at it, they're both covering 2 pi radians in the amount of time that they're spinning for. I don't know however long that is, but they're both covering 2 pi radians. So that's where stuff starts to feel a little bit weird, feel a little bit awkward. But they're covering the same circular path, and we can picture they're like kind of connected maybe by like a spoke or something. But they're covering the same amount of radians in the same amount of time, so these 2 objects will have the same angular velocity, which again, kind of weird, kind of tricky to think about, but yeah, so same amount of radians in the same number of seconds. So yeah, if we're at the same radius and we're connected. All right, and then finally, the last one that we want to define is our angular acceleration. But first, let's talk about acceleration. So we said linearly, acceleration is when we change our velocity over time. So if we're changing the velocity, we're accelerating. And the acceleration just tells us the rate at which an object's velocity is changing. And we're going to measure that in meters per second, or as we called it, meters per second squared. But I kind of like meters per second. It helps us think how many meters per second are we changing each second. And then we have angular acceleration. So an object can speed up while it's spinning. It doesn't always have to spin at the same rate. So the angular acceleration, or our symbol for it will be alpha, this little a, it'll tell us an object's change in angular velocity over a change in time, or the rate at which an object's angular velocity is changing, and we're going to measure it in radians per second, or radians per second squared. So this one, I couldn't really figure out how to make the Desmos thing speed up, except for unless you actually do it and be like, oh, it's changing its rate. So I just took a quick video. Well, I didn't take it, I inputted a video. So we have these bats that are connected to this motor, and they're speeding up over time. They're not always spinning the same rate. He has it hooked up to this motor that's going to keep on and making it spin faster and faster and faster. Eventually the video gets weird because the frame rates, whatever, but it's speeding up over time. So we have this angular acceleration of these bats. I also had a video of Beyblades, but then I didn't put it in there. But this guy had a Beyblades lit, like he had like a garbage can, and then he put like fuel on it, and then the Beyblade set on fire or whatever, but it doesn't matter. But yeah, so then we have our linear equations that we're used to for telling us, hey, if we're accelerating, how does our velocity change over some amount of time? Or if we're accelerating, how does our position change over time? So we had equations that helped us out with that we're really used to. We're used to using those equations. We have the same exact equations for the angular motion. All we have to do is take our linear variables and then replace them with the angular equivalent. So we said, hey, the velocity tells us how fast we're moving. The angular velocity tells us how fast we're moving. So we just replace the variables in the linear equations with our angular coparts, I guess. I don't know if that's the right, whatever. But our analogous angular pieces, and then we'll get the same equations. We'll just be able to use them for rotating objects instead of linearly moving objects. And so the same trends, we're following the same equations, we're following the same ideas, the same trends apply too. So if we were looking at like a linear situation, we said an object is at rest 2 meters from the origin. What would these graphs look like? What would these position versus time, velocity versus time, acceleration versus time graphs look like? Well, we can do this one pretty easily. We say, well, it's 2 meters from the origin. So it just kind of has this constant position, a 0 velocity, and then a 0 acceleration. It's not moving, it's not changing its meters each second, so velocity is 0, and then if we're not changing velocity, we're not accelerating. But so yeah, we can do this with a linear graph, a linear idea. And we can do the same thing for an angular idea. We can say, okay, an object on a disk is at rest 2 radians from the origin. What would these graphs look like? Well, if I'm thinking about that, it's at rest, so I'm at 2 radians from the origin, and I'll remain 2 radians from the origin. So I have this constant angular position, a 0 angular velocity, and then a 0 angular acceleration. So it's kind of the same idea. We're saying, hey, instead of sitting at some position linearly away, let's do that. So instead of just sitting at some linear position away from the origin, we're just saying, oh, well, we're some amount of radians away, and we're not moving. So we have those graphs for a constant position. And then we can kind of change it. So we said, okay, well, we can change our velocity. So if we're looking at this linearly, an object is moving to the right with a constant velocity of 3 meters per second. Well, we can do that too. We said, okay, well, we know that this slope of a position versus time graph is going to tell us about our velocity. So if we kind of did that, we can say, well, we have this constant slope, we have this constant velocity, and we have a slope of 3 meters every 1 second. So 3 meters in 1 second, 6 meters in 2 seconds, 9 meters in 3 seconds, 3 meters per second. And then we said, well, we have this constant velocity, so we have this constant line at 3 meters per second throughout time. And if our velocity is constant, then we have the 0 acceleration because our velocity is not changing. So then our angular counterpart, what this would look like angularly, is let's say a disk is spinning counterclockwise with an angular velocity of 3 radians per second. So it has this constant angular velocity of 3 radians per second. So every 1 second, it's going 3 radians. And if we kind of track that out, we'd see again, this is just a linear line. The velocity would be constant, and the angular acceleration would just be 0. So we'd have the same exact idea. We'd go 3 radians every 1 second. It would be happening at a constant angular velocity, and the acceleration would just be 0 because it's not changing its angular speed. And then finally, just kind of in general, we're saying an object starts at the origin at rest. It slowly increases its speed to the right. So this would look like, okay, well, we'll do it because we're used to it. We're slowly increasing our speed. So we see this slope over here for position versus time is gradually increasing. We see the slope goes from like a 0 slope to increasing to getting that, right? So going from flat to kind of increasing slope. We see that the velocity is changing. The velocity is increasing over time. So we see we start with a 0 velocity and it gets more positive as we go. And then this acceleration is constant. We are gaining the same meters per second every 1 second. And so we said, okay, a disk starts from rest. It slowly increases its angular velocity in the counterclockwise direction. That would look like the same exact trend. We'd have the same trends where we'd say, okay, we start off, we're not changing our radians per second. Our radians over time is not changing, and then that slope increases. So then we get this increasing change in radians over time. We start to cover more radians over the same amount of time. Our angular velocity goes up. We see, okay, we're starting at 0 to an increased angular velocity, and then our angular acceleration is just going to be constant. But so we see the graphs, they look the same way. We can think about the graphs in the same exact way, and the same trends apply. When we looked at linear kinematics, we said, okay, the slope of an angular position versus, or we said with linear, the slope of position versus time is the velocity. It's the same idea. The slope of an angular position versus time graph is going to tell us the angular velocity. And kind of taking it to the next step, the slope of an angular velocity versus time graph is going to tell us the angular acceleration. So we saw that with linear. Same thing applies for rotational or angular. And then kind of going backwards, going from right to left, I guess, the area under an angular velocity versus time graph to a certain time will tell us the angular displacement at that time, and the area under an angular acceleration versus time graph to a certain time will tell us the angular velocity at that time. So when we were dealing with linear stuff, we said, oh, we can figure out the area underneath the velocity versus time graph. That'll tell us the displacement. Same thing applies when we're dealing with rotational objects. So then one other thing, if we want to go from an angular kinematic idea or variable to a linear one, we're really used to doing that. We do that a lot in math ever since, I don't know, whenever you learn about circumference. You do that in math. So you do it a bunch, but you're not thinking about what you're actually doing. So if we think about going one rotation around a circle, if we kind of have this over here. So if we think about one rotation around a circle, we learn in math class that one rotation is equivalent to 2 pi radians. And if you're ever given a circle and you say, okay, this circle has a radius of 1 or something, you're saying, okay, well, I can figure out the circumference. I can figure out the linear distance in meters of that circle. And you just use the circumference equation. You say, okay, I have this equation that says your circumference is equal to 2 pi r, and that's for one full rotation. So what you're really doing is saying, oh, my linear distance that it's going is equal to my angular distance times the radius. You're just using an angular distance of 2 pi when you're looking at one full rotation, but you can do this for any amount of radians, for any degrees of radians. So yeah, we have the same exact trend. It follows through for all of our variables if we want to go from linear to rotational or rotational to linear. So we have, hey, let's take our linear piece. That's going to equal the rotational equivalent times the radius. And we can see, does that make sense? So if we're looking at a situation, if we increase the radius, does the particle cover more linear distance? So let's look at this. So we can change up our radius. So here would be like 0 radius, right? So let's start with a really low little circle with a radius of 1. Okay, so if we go 2 pi radians, let's see, or actually, sorry, I want both of them at the same time. So if we look at both of these, both of them, the red one and the blue one, are going 2 pi radians, but the red one, it definitely covered more distance. If we think about how far it went way further. If we kind of think about unraveling the circle, it went a lot further in terms of meters. So they both covered 2 pi radians, but we see this is tied to the radius. If our radius increases, then our linear distance that we traveled in meters went up. So that checks out. This totally makes sense. This totally works. Now let's think about it with the velocity. And we kind of mentioned it before, but both of these objects have the same rotational velocity, the angular velocity. They're both covering 2 pi radians in the same amount of seconds. But this red one, if we think about linear velocity, the red one is covering way more meters in this amount of time. So we see again this trend where if we increase the radius, then our linear piece is going to increase. We're going to have a greater velocity, a greater linear velocity, because it's covering more meters in the same amount of time. Even though they have the same rotational velocity, the 2 pi radians in some amount of time, I guess I could just leave it like that. The red one is definitely covering more meters in that same amount of time, so it has a larger velocity. All right, and then now we're saying, okay, we have this idea of angular acceleration. Well, how could we actually make an object angularly accelerate? So if you were like holding a wheel, what could you do to angularly accelerate it? And we've done that around before. We did that in class. We said, okay, if we have this wheel, what we have to do is we have to apply a force some distance away from this axis of rotation. And if we want to get technical with it, if we want to use our physics terms, applying a force some distance away from the axis of rotation, that's just a torque. So what we're saying we have to do in order to angularly accelerate an object is we have to torque that object. So torque is kind of like our rotational equivalent of force. Before, when we forced objects, we had them accelerate. Now, if we torque objects, they will angularly accelerate. So it's kind of the same idea. It's just, again, taking our linear piece and saying, what is our rotational equivalent? So torque is going to be our rotational equivalent of force. And when we think about torque, if we want to think of like a definition for it, we can think about it as a force that causes a rotation. So a force that will make an object rotate. And if we see over here, we kind of have this lever and this fulcrum. The GIF is applying a force at some distance away from the fulcrum, from the pivot point, and it's causing this lever to rotate. It's causing this lever to angularly accelerate. And if we're thinking about the factors that are going to affect torque, we have our equation up here for torque, saying this torque is equal to R times F, or RF sine theta. And the factors that are affecting it, that are kind of building up this equation, is going to be the amount of force, F. So if we apply more force, we'll have more torque. The distance from the pivot point to where the force is applied, that's R. So the distance from the pivot to where the force is applied. And then another thing that matters is going to be the angle that the force is applied at. So we see down here in this GIF, if your distance from the lever, or from the focal point or the pivot point is like this, if you're forcing it parallel to that lever arm, it's not going to rotate, right? So when you go to doors, you open up a door and you push it perpendicularly. You don't push the door into the hinges. That won't make it rotate. So here we see, okay, the piece that's making this thing actually rotate is going to be the perpendicular component. This component over here is the piece that will make it actually rotate. The parallel piece will do nothing. So that's why we have this R perpendicular, or we have this sine theta to tell us, hey, we care about the piece that is acting perpendicular to the fulcrum, or to the pivot. So then we want to think about what factors are actually affecting the torque's ability to angularly accelerate it. We know that torque will angularly accelerate an object, but what factors are actually affecting that? So we can kind of set up, here's this little like online mini lab. So if we increase the mass, we're increasing the torque, because we're forcing it more away from this pivot point. But if we think about, okay, what other things can we do? We can change the actual mass of the pulley, and that'll kind of slow us down a little bit. And we can also increase this distance. It is a way that all the mass is kind of concentrated at. That'll slow us down a little bit more. We kind of see these graphs. This is kind of hard to do though. Let's see. We make it really small. So these were, oh wait, just kidding. That'll be a little bit easier. I don't know if you can see, but this one has a greater velocity, which means there's a greater angular velocity. This one, the position changed a little bit quicker. But so the factor that's really affecting that is going to be called our rotational inertia. And we're going to use the symbol capital I to represent that, so rotational inertia. And it really is just describing how the mass of an object is distributed. So it's really telling us, hey, how much mass do we have and where is that mass? So what we have is the factors that are going to affect rotational inertia is the amount of mass that we have. If we have more mass, we have a larger rotational inertia. And if the mass is further away from the axis of rotation, that means that we have a larger rotational inertia. So we talked before, we said, okay, different objects have different distributions of mass, which means they have different rotational inertias. And we kind of messed around and we had these different, these different objects, these common shapes, and we said they all have this different coefficient in front. But what's similar is they all have mass times r squared, the distance from the pivot point squared. So even though they have these different equations, we won't have to know them. If you're going to use them on the AP test, they'll be given to you. So you don't need to know these, but it just kind of helps us think, okay, well, the difference in how this mass is distributed is going to affect the object's ability to rotate. So if we kind of look at the cylinder versus the hoop over here, the hoop, most of the mass is really far away. So we see it's going to have a larger moment of inertia than the cylinder, because the cylinder, the mass isn't all concentrated at the edges. The mass is kind of all spread out throughout the cylinder. So this one has a lower moment of inertia, meaning it'll be easier to rotate than the hoop. So again, you don't have to know the actual equations for them, but it helps us to kind of think about it. This idea that if the rotational inertia goes up, it means that our mass is either larger or it's more further away from the pivot point. And then, so we have this idea now. We have torque, we have rotational inertia, and we have angular acceleration. We can link these all together, and we can link them together using Newton's second law for rotation. So we talked about Newton's second law for linear moving objects. We have this force, net force equals mass times acceleration. We have the same thing here for torque, or for angular acceleration. We have the way the equation's written on the AP equation sheet is this angular acceleration equals our net torque over rotational inertia, or the way that we're more used to seeing it is torque net equals rotational inertia times alpha. And this is the same trend that we saw with Newton's second law, this idea that if we increase the torque, the angular acceleration will go up. If we increase the rotational inertia, it'll be harder for us to angular accelerate, and our angular acceleration will go down. So yeah, same trends just like we had before, but now it's for rotating objects. And then kind of a big idea that we had when we were dealing with linear objects was what happens if the net force is zero? Well, if the net force was zero, we had these objects that were in equilibrium, meaning they weren't accelerating. There was no acceleration. Maybe they were moving with a constant velocity or not moving at all. But we have the same thing if the net torque is equal to zero. So if the net torque is equal to zero, then our object is in rotational equilibrium, meaning that it's not angularly accelerating. So we can kind of look at a quick little example of this. If we think about this situation, okay, we have 10 kilograms, that's 1, 2 kind of deviations away from the pivot point. Here we have 5 kilograms, that's 1, 2, 3, 4 away. If we remove these little things that are holding up the seesaw, we see, oh, well, we're going to balance out because the torque on one side, the positive torque, is going to be canceled out by the negative torque, and we'll have this balance. We'll be in this rotational equilibrium. If we add torque to it, now we have this net torque, and our system will rotate. Yeah, kind of fun. And yeah, so situations with zero net torque, oh wait, actually we'll talk about this first. But so then we also have to define this quantity of center of mass. So we kind of, when we talk about objects in this class previously, we said, okay, well, center of mass, let's not really worry about it. Let's just say, like, if we have a ruler or something, let's just call it a massless ruler. But in real life, objects are going to have mass. And this has a lot of consequences to our rotational motion. So we have this idea that there's this position of all objects have this position called their center of mass. And we can just call this point, we can assume that this is a point where all of the mass is concentrated. So if you support something through its center of mass, that's kind of all you need to do to lift this object up. So the gravitational force is going to act through the center of mass, and if the object is not pivoting at its center of mass, then the gravitational force can cause a torque. So here we have this situation, we have this ruler or this stick or whatever. Here's a pivot point down here. Well, if we have this like nice uniform ruler, we know the center of mass will be just at the middle. If we wanted to support this thing, we know from just everyday life, if we want to pick this up, we'd have to support it from the middle. So we'd pick it up through its center of mass. But if there's nothing supporting the center of mass, we have this gravitational force acting through the center of mass, which is some distance away from a pivot point, which means we have this net torque acting on our object, which will cause it to rotate. So let's look back at this tensegrity, this idea. So we know that it's not angularly accelerating, so we know that the net torque has to be zero. But if we're thinking about it, what forces are causing the torques? Like we have these torques, but like, and we have these forces, what's causing this thing to balance? What's causing this thing to not rotate? So I kind of redrew it here. So yeah, we redrew it just to make it look a little bit better. So if we think about it, we can circle our object and think about, okay, well, what forces do we have acting on it? So we see we definitely have this contact force from this string. We have a contact force from this string. But if we're thinking about it, if we kind of cut this string here, the top object, it'll rotate around that pivot point. So we can kind of say the pivot point, the axis of rotation, is through this string that we have over here, this string that's kind of in the middle. Our object will rotate around that. So we say, okay, well, we have this tension force, and we know that tension has to pull. Tension isn't going to push. So tension's pulling this object back in. which would cause a clockwise torque. So we'd have this torque from the tension over here because we have a force that's acting some distance away from our axis of rotation. So we have this torque, but we know, hey, like, we need another torque. This thing isn't rotating. This thing isn't angularly accelerating. So where is that force coming from? Right? We don't have any other forces over here. But we do. We can say, well, the object, the way that this object is configured is so that its center of mass is over here. Most of the mass of this object is concentrated on the side to the left of our axis of rotation. So this has a center of mass that's to the left, and we say the gravitational force is going to act through the center of mass. So if we picture our axis of rotation, we actually do have a force that's acting to the left of this axis of rotation that's causing a torque that would make this thing spin counterclockwise. So we actually do have a positive torque and a negative torque. So if we look at the situation, we say, hey, the net torque is 0. This torque is coming from the tension, and this torque is coming from the force of gravity. If we were to add those up, we'd say, oh, well, the torque from the tension has to equal the torque from the gravity, so they're going to equal each other. And then we could do some math if we wanted to figure out the tension. We'd say, oh, well, I can figure out the force of gravity of this object. I can figure out the distance from the pivot point, distance of the pivot point for the tension force, and then you could solve for the tension force, but whatever. But yeah, so we have this balancing of torques because of how the center of mass is laid out in this interestingly shaped object. All right, and then kind of some consequences, some final things, some consequences of torquing an object. If we torque an object, we know that it's going to angularly accelerate. If we have a net torque, we're going to have an angular acceleration. And if we have an angular acceleration, it means that the angular velocity is going to change. So changing the angular velocity is important. There's a couple of things that change if we were to change the angular velocity. So we got these two quantities. We have the rotational kinetic energy, and we have angular momentum that are both based on the rotational velocity of an object. So first we'll talk about rotational kinetic energy, and this is nice. It's kind of a cool idea because it works like energy before. So when an object is rotating, it has rotational kinetic energy. So before we talked about translational kinetic energy, which is the energy of motion if an object is moving. This is the energy of motion if an object is rotating. So if an object is rotating, it has this rotational kinetic energy. And yeah, so what we can say is before, if we were going to change the energy of an object, we said we had to force it over some displacement. We had this work equals force times displacement. So the same thing applies for rotational kinetic energy, but with our rotational variables. So if we were going to torque it over some angular displacement, then our object will have a change in rotational kinetic energy. And some ideas with that, usually it'll be pretty obvious if our object is rotating. It'll tell you the object is spinning, but there's one case that's a little bit less obvious, and that's when we have friction in our system. So if we have a round object and it's sliding on an object with friction, it'll begin to roll because this friction is acting as a torque. We kind of look at this situation down here. Here's the center of rotation of our object, what our object would want to rotate around. And we said, okay, well, that's some distance away from this frictional force. We have this frictional force that's acting perpendicularly to this center of rotation. Or what we could say is it's acting right parallel to the surface, and the distance to the center of mass is perpendicular to the surface. But so yeah, we can say, hey, we have this force acting at a distance, it's acting perpendicularly, which means that our object will be torqued, and if we're rolling, it'll happen over some angular displacement. So this will give our object a rotational kinetic energy. And this is just kind of a quick little side thing, but I don't know, it's kind of cool. It's kind of cool to think about. So friction is going to cause our objects to roll, and friction, we said, is based on the coefficient of friction and the normal force. So a cool consequence of this is bowling. Back in the days when we used to be able to bowl, we have, this is something that I totally didn't know about until I watched this cool like Vox video. I don't know, I'm not going to make you watch it or anything, but it's really cool if you're interested. Hidden oil patterns on bowling lanes. It's a very cool video. But apparently all bowling lanes, or with the Professional Bowling Association, there's different patterns that you have to like learn and get used to when you're bowling, because yeah, these oil patterns are going to change up how much your ball can roll, which will change up how much spin you can put on it. So these dark parts over here are spots where we have a lot of oil, and then if we have the lighter parts, or the parts that don't have any blue on them, that's parts where we have no oil. So oil, we know, is going to be very slippery, and it'll decrease the coefficient of friction. So towards the beginning, we'll watch a few bowling videos, but if you've ever bowled, you know, okay, in the beginning, the ball is kind of sliding. It looks like it's slipping. It doesn't really look like it's rolling. And that's true. That's what's happening because we don't have a lot of friction, so we don't have a lot of torque that's causing this object to rotate. But then towards the end of the lane, that's where we get a lot of friction. So we'll have just kind of normal wooden surfaces interacting with our ball. There's more friction. There's a higher coefficient of friction, which allows our object to spin more. And that's where you have the professionals. That's where their balls really break. That's where the balls can start to spin and we start to get kind of these hooks. So I just have some trick shots here. But there it was kind of sliding. And we see at that point, once we get like more towards the end of the lane, that ball can really start to rotate. It can start to spin and it can kind of start to grip that surface and we actually get this spin. And this one's cool because right, this pin hits that pin. The next one, the guy goes, yeah, over the chair is kind of a good example. But yeah, so towards the end of the lane, did you see how much that hooked? That's crazy. Oh, I guess they're going to show it again. But yeah, before it was kind of moving straight, it was sliding. It wasn't really able to grip that much. But then towards the end, we get that spin kind of kicks in because that frictional force is stronger. That's kind of cool. I don't know what the last one is. I didn't watch it. 3-ball split conversion. Oh, what? Oh, he's doing... Whoa, that's cool. Well, that doesn't... Oh! It's not really helping my point, but that's pretty cool. But yeah, so friction, whatever. Friction's going to increase our rotational velocity, or rotational kinetic energy. And then just kind of a consequence of that is if we were going to say, hey, let's put this ball on the top of the ramp. In this case, let's say that the ramp is frictionless. So if it's frictionless, we'll kind of have that nice like oiled part where our ball doesn't really spin that much because there's no friction that's going to cause torque. So we'd say, okay, well, we start off with this gravitational potential energy if we're looking at this LOL diagram, and then all of that gravitational potential energy turns into kinetic translational energy. At the bottom, it's not spinning, and it's just kind of moving. So that's what situation that we're more used to. But sometimes they'll hit us with situations and say, okay, the ramp has friction, and the ball will roll. So if it does happen like that, and we say, okay, we start out with gravitational potential energy, and then we end up with, we're still moving at the bottom, but now we have this other piece. We have this rotational piece. Our object is spinning, which means it has kinetic rotational energy. And when we deal with this, energy still has to be conserved. So a consequence of that means that our ball is actually going to be translating slower. It's going to have a lower velocity because some of this energy is now tied up in kinetic rotational energy. So it's just kind of a cool consequence. It'll be moving slower because it has kinetic rotational energy instead of pure translational kinetic energy. Then the last little thing we're going to talk about is angular momentum. So before we said, okay, if we wanted to change the momentum of an object, we have to force it over some amount of time. And we kind of had the same idea here, but just angularly. So if an object is torqued, it has an angular acceleration. If it has an angular acceleration, that means its angular velocity changes. And if the object's angular velocity changes over some amount of time, that means its angular momentum is changing. So if an object is torqued over some period of time, its angular momentum will change. So our symbol for angular momentum is L, and we see over here this equation. If we torque it over some amount of time, then we'll have this change in angular momentum. And angular momentum is just a property of the object's rotational motion. Just like how momentum was a property of the object's translational motion, the angular momentum is just a property of the object's rotational motion. And it's going to be based on the mass equivalent and the velocity equivalent with rotation. So it's going to be based on the rotational inertia and the object's angular velocity. And the angular momentum is conserved in collisions. That's a big idea. So when we talked about linear momentum, the collisions that we were looking at was really like, hey, we have two objects that are interacting with each other. Usually with angular momentum, we can have two objects interact with each other, but a more common situation is objects will actually change their configuration. And we said that the rotational inertia is based on the configuration of the mass. So how much mass do you have and where is that mass in your system? So yeah, usually if we have a collision with angular momentum, it'll really be, hey, we changed up the rotational inertia. Our rotational inertia changed. So if we look at this GIF down here, they start out, most of their mass is concentrated further away, so they have a larger I and a lower omega. Then when they bring their leg in, she's increasing her angular velocity by decreasing her rotational inertia. Most of that mass is closer to the rotation axis. And then a final little thing, a cool little note about that is when we have like planets that are moving or planetary motion or planetary orbits, they're usually not circular. We treat them as circular. The Earth's is pretty circular, but some planets we have more of an elliptical motion. So an idea with that is if we have like a planet that's orbiting a star, we can look and say, well, this is actually one of like Kepler's laws that dictate this. But if we're closer to the mass, we're actually going to be moving faster. If we're further away, we're going to be moving slower. And that's a consequence of conservation of angular momentum. So we see here, when we're closer, we have most of our mass in the system is distributed closer to the rotation axis. So we have a smaller I because the rotational inertia is lower. It's concentrated closer to the rotation axis. So we have a lower I, which means we have a larger omega, a larger rotational velocity. When we are further away, our I's increased. So that's kind of like if we held our hands out while we were spinning. We're making our mass less concentrated. We're putting our mass further away from the rotation axis. So we're going to increase the I, which means we'll be spinning slower, so our rotational velocity has to decrease. So that's just kind of a cool consequence. And yeah, hopefully that was a decent review of these ideas. Then I'll hook you up with some practice questions and some free response questions.